Okay, so we had to prove three properties, 1 bar, 2 bar, and 3 bar. 3 bars was very easy, so you didn't really have to prove anything. 2 bar had a long double conditioning proof. Okay, and following the same proof, I'm asking you to prove 1 bar, except that I'm doing it in a special case, k equal to 1. But as I said, the general case can be done except that instead of a double conditioning, you have to use a k plus 1 fold condition. But you can do that as well if you want. Okay, but it's the same proof. It's just the writing is more complicated. So this completes the proof of the Thiening theorem. The rest of today, we are just going to give a summary of homogeneous Poisson process, what we have learned. So this actually ends our coverage of homogeneous Poisson process, and we'll just summarize what we have learned instead of starting something new. So our next topic would be discrete parameter Markov chains on a countable state space. So that's we'll start from next week. So this week will be just summary of this homogeneous Poisson process, what we have learned. And of course, there'll be discussion on Friday on whatever questions you have on this topic. Okay, so the way we started is that we started with IID inter-arrival times, exponential alpha, and then we defined the arrival times as the 0th arrival time being the random variable 0, and then the mth arrival time for every positive integer m was the sum of first m inter-arrival times. Then for every non-negative integer t, nt is the count of number of arrivals up to time t, which is given by this expression. And we proved that this follows, and since these are IID exponential alpha, this follows a Poisson with parameter alpha times t, with the convention that when t is 0, then this is Poisson 0, and Poisson 0 is the random variable 0, probability 1. Okay? This is what we called a homogeneous Poisson process with rate alpha or intensity alpha. The way it looks, we do the graph. So it starts at 0, stays at 0 all the way up to and before the first arrival. Exactly in the first arrival time, it jumps to 1. Then it stays so at 1 all the way up to before the second arrival. At the second arrival, it jumps to 2, and it stays there all the way up to and before the third arrival. Then it jumps to 3, and so on. This goes on. The summary of this is that for every non-negative integer n, nt takes the value n if and only if the nth arrival happens on or before time t, but the n plus 1th arrival happens strictly after time t. This equivalence of these two events we have used quite a few times in this course. And namely, it helps to go. So note that this, okay, so this is the thing that we have used, but I would like to summarize it again, is that this is a statement about a discrete random variable, nt, right? For every fixed t, there is a discrete random variable. Whereas this is a statement for every fixed n, this is a statement about two continuous random variables. So this is a way to switch from discrete random variables to continuous random variables, or the other way around. So this we have used quite a few times in this course so far. Then we proved that if you start with a homogeneous Poisson process with intensity alpha, and fix a t naught bigger than or equal to 0, then the stochastic process n tilde t, which is n of t naught plus t minus n of t naught, is also a homogeneous Poisson process with intensity alpha. And this process is entirely independent of the process, original process n up to time t naught. By the way, the theorem that we proved only had n t naught in here, but then I gave you an exercise that asks you to show that n tilde t is independent of the process n all the way up to time t naught using the Markov property of n, the process n. Okay. So therefore, we are actually using the exercise, we actually proved this thing. And the interpretation of this result, as I said, is you join office at time t naught. All you care about is this n tilde process. Since you join office at t naught and reset the clock at 0, this is the process of arrivals that you observe. Whatever you observe is independent of whatever you haven't observed, namely whatever has happened before you joined your office. That's what the statement of this result. Then we gave this characterization result of homogeneous Poisson process. Namely, we showed that a stochastic process n dash t is a homogeneous Poisson process with rate alpha if and only if it has independent increments, the stationary and Poissonian increments, and it starts at 0. This characterization is extremely useful, as we have seen. We have used it to prove the Thirring result, and I've given you an exercise to prove the superposition result. That also uses this theorem. So this is a handy way of proving or verifying that something is indeed a homogeneous Poisson process. And if you always have to start from the definition of homogeneous Poisson process, namely with IID exponential interarrival times, it will be too cumbersome. So therefore, this result is extremely useful, as we have already seen in this course. Then we gave many properties of a homogeneous Poisson process, and I'll only like to mention a few of them. One of them was the order statistic property, which we stated and sketched the proof for you. So the proof is actually left as an exercise for you. So if you fix a t, which is a positive real number, and an n, which is a positive integer, then given nt equal to n, the conditional distribution, so given that n arrivals have come up to time t, the conditional distribution of the times of the arrivals, okay, is same as, so obviously S1, okay, so this is a typo. I copy pasted from a typo, I think. Okay, so this should be S2. Sorry, I'll correct it. So anyway, the conditional distribution of S1, S2 all the way up to Sn is same as the unconditional distribution of the order statistics U bracket 1 less than U bracket 10 all the way up to U bracket n based on a random sample of size n from the uniform distribution on 0 to t. So in other words, the conditional probability density function of S1, S2 all the way up to Sn, there is no typo here, given that nt equal to n is just this expression here. Okay? And as I said, this is a manifestation of lack of memory property of exponential distribution. What we are saying is that if it is given that exactly n arrivals have come up to time t, then the conditional distributions of the arrival times is uniform more or less. So the fact that exactly n arrivals have come up to time t does not give any extra information about the arrival times, except that they are all between 0 and t uniformly. Of course, the arrival times have a natural ordering. S1 is strictly less than S2, S2 strictly less than S3, and so on. That has to be honored, and therefore, we just have to look at the order statistics from uniform 0 to t distribution. That's all. Except this ordering constraint, there is no extra information about the distribution of the SIs. Conditional on nt equal to n. So this is order statistic property. Then of course we learned about superposition and thinning. So superposition is when you have k independent homogeneous Poisson processes and you superpose them. So you look at all the points, Poisson arrival points together, and that amounts to essentially adding these NITs. If you look at this superposed process, this is another homogeneous Poisson process. Since the original processes are independent, it's very important that the original processes are independent. And of course, the rate is the sum of the rates of these individual points. So then we learned about thinning, which was essentially if you start with a homogeneous Poisson process with rate alpha, and then each arrival survives with probability P, independent of each other and also independent of the arrival process. Then the thin process, namely the process of survived arrival, is also a homogeneous Poisson process, and the rate is P alpha. So this is more or less a summary of what we learned about homogeneous Poisson process. And then finally we have the second homework. It has been uploaded in the course website. And as usual, you start solving it after going through in details the lecture 6 videos and slides. And its due date is September 30, which is exactly 2 weeks from now. By the way, the first homework is due today. Most of you have already submitted it. In case you haven't, please submit it by today, by email, as one PDF file. Same applies to this one. You have to email me as one PDF file and by September 30. Okay, so this concludes this lecture.